Just looking over some of the John Deere scope measurements that I took. Um, this is a capture I took of the no start, the unit we're working on. Red is your crankshaft signal. Yellow is your um, ignition, or your injection. I'm going to bring up a notepad just to keep track of this. So we're going to go on the no start. So we're going to label this one no start. I'll label one known good. So I have two captures I'm going to go over on this. Okay. So, so we'll zoom in here. So let me zoom out a little. There's a little trick to do to get kind of good captures on here. So it's a four-cylinder engine, um, and I'm probed into the common power B plus, and injector one. You can see these are injection signals. That's because it's since it's a common power input, you're going to pick up the middle injectors, but the one that doesn't show the pulsing is the actual one we're going to measure off of. Okay, so let me zoom in here. So as we know, the auto ignition cycle takes place over 720 degrees of crank movement and only 360 degrees of cam movement. Just to refresh, your cam is going to control the four cycles of the engine: compression, power stroke, um, exhaust stroke, and intake stroke. Those four cycles happen over 720 degrees, each one being 180 degrees. So if I take my cursor, and this is the no start, so if I get some cursors and I mark it on the beginning of this yellow channel 1 injection event, and I mark it on it cylinder 1 injection event happening again for a second time, that will be 720 degrees of rotation. A certain cylinder firing once, all the cylinders firing in between that, and then that cylinder firing again. You're starting again, starting and stopping in the same spot with your cursors. And then I'm going to hit mark cam. I can also hit mark cylinders, so let's just hit mark cylinders. I got a 4-cylinder. And it's either one. So we're marking cylinders. Okay, so we got 1, 3, 4, 2. And we have our 720 degrees up here at 229 RPM. Notice on the crank gear, you can see this spot. This is a 40 tooth crank. So every tooth is about 9 degrees. Okay, it's a 40 minus 2. So this index in the middle here is indicating, sometimes it's top dead center, sometimes it's some degrees before top dead center, but nevertheless, this is an index mark, so the ECM knows where it is positionally. If you just had all teeth, it wouldn't be able to identify a starting and stopping point on the crank. That missing tooth, that's just an index, okay? So if we measure off of that, comparing that to the cylinder injection event, we can correlate timing between engines, a known good and a bad engine, and we can compare the timing. The fact that this scope does calculations for degrees of rotation only makes the job easier. So that said, we can count over here that after the index, my ignition event is starting on this cursor. We'll count the teeth. So we got 1, 2, 3, 4, 5, 6. It's the 7th tooth after the index. So we know it's the seventh tooth after the index on the no start. So we'll write 7th tooth. And then let's find out how many degrees actually that is. So if I get the degrees, so after the index, we are about 55.7 degrees. 55.7. And I'm going to get a couple measurements here. It's always best to get it in a couple spots and then take the average of that. So let's find a spot here again. I'll get 4 cylinders. I'm going to get it so I see the 2 cylinder ones. I'm going to get cursors. I'm going to mark. I'm going to bookmark cylinder 1 events. I'm going to hit mark cylinders. I get my 720 at 234 RPMs. We are again at 1, 2, 3, 4, 5, 6, 7th tooth. And I'm going to go right here. And we're looking at about 56.4 again. 7th tooth, 56.4. So we're going to keep 7th tooth. We know that, 56.4. So just to be safe, let's go 56.6. 56.6 will be our, we'll space that out. Okay, so now let's pull up our known good. We'll go to known good. Here's my known good. Now, actually, let's do this one. I have a better one. Data, I think I had crank and run. That gives me 2 better spots here. Okay, so let me zoom out. Let's take a zoom window. You can see the indexing marks here. Channel 1 now is my crank. So we'll zoom in. Oop. Zoom undo. Get my zoom window. We'll move in. I'm going to pull off channel 1 for a second, and we'll get cylinder 1. Again, you can see this is my cylinder 1. These are the in-between injection cycles. So we'll get some cursors. Now, one thing I do want to say on this waveform, I didn't set my voltage high enough on my crank probe, so the voltages are going to be off. Actually, I didn't set any of them high enough. But the signals, no matter what the voltage reads, it's fine. We're looking at degrees, not voltage levels. So, so I'm on cylinder 1 firing, and then cylinder 1 firing again. We're going to return. Okay, we got about 1810 RPMs. Now, if I bring up, you can see how these waveforms come to a square at the top. The reason that is because they're getting chopped off on voltage wise. I didn't have the right probe. I wasn't using the right voltage probe. So you could picture these teeth coming up to a point, like a sharp tooth. And just like a triangle, if you took a line and drew it down right from the center, the point down, you would be exactly in between that. So we can just put a cursor in between, like right centered, and you would be exactly where the point of the tooth. There's no, I don't know if I'm describing it right, but if you took a point, marked the pin, and then went down to the wider part, you'd be exactly center. Well, this is the wider part. So as long as we mark the center there, but let's show this. Already we are on this one. We are 1, 2, 3, 4, 5. And I can 1. And actually, I want to show you where we are here. Let me put this up and this down. You can see I'm going down right here. 1, 2, 3, 4, 5. So already with a 5th tooth out on the known good. So we'll write 5th tooth, and what we will do, we will get our cursor, and we are going to go right in between that, and we're going to see 39.1 degrees. We are at 39.1 degrees. 39.1. Okay, and what we're going to do, we're going to zoom out to full, And we are going to zoom out a little more, and we are going to grab another window right about here. We'll go one more time. We'll pull this into here, and we have another chunk. It's good to get two measurements, so I'm going to get cursors, and I'm going to start there, and I would expect to see that we're on the 5th tooth again. And we are 1, 2, 3, 4. We're on the 5th tooth. I'm going to hit mark cylinders. And I'm going to mark them. There's my 720 at 1805. That's how you know the software is doing, the capture is good because it corresponds to the 1800 RPMs of a good running generator. And now we are going to pull our cursor in over to here. We're going to go right in the center of that where the peak of the tooth would be. And we are at 38.4. So let's go 38.4. 38.4. Okay. So I would say 6, 7. So we'll just say, just for good luck, 7. We'll go 38. 38.7. We'll say 38.7. 38.7. Okay. So let's say 56.6 minus 38.7, and we will bring up my software, bring it over to here. Okay, so what were we saying? 56.6 minus 38.7 equals 17.9, about 8. I'm just going to say 18 degrees off. Now, we know we have a 40 tooth reluctor wheel. So let's do this. Let's blow this up. Take a zoom window over here. And let's take our cursors and we will go center here. And we go center there. Let's shut off our ignition. And I'm going to hit mark 360. Let me get in the center of that one more time. Oh, I didn't grab the center there. So, boom. Mark 360. And let's find out. So there's my 360. And again, even marking the 360, we get our 1804 RPM. So we know that's right. So let's go to the center of that tooth, just to show you. Say right about there. 9.3 or so, and let's just go to another one over here. Let's go right here, center there, about 9.1. So this is a 40 minus 2 crankshaft reluctor wheel. What that means is if it's 9 degrees between teeth, we could calculate 360 divided by 9 equals 40. Okay, so let's see if that matches. We're kind of reverse engineering this to see if to verify our information. Okay, so starting here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, and then you'd have 39, then 40. You're missing 2 for the index, making a 40 minus 2 reluctor wheel. So we're going to put that on our map. 40 minus 2 reluctor, and that would be 9 degrees per tooth, Okay. EG per tooth. And we are 7 teeth and 5 teeth. So 2 teeth off. At 9 degrees per tooth. And you know what the answer is. 18 degrees off electronic timing. So that's where the electronic timing coming, or ignition. There is, even though it's a diesel, there is ignition taking place. Timing. And I'm making that delineate, and that matches that 18 degrees here, matches that. Okay, so we are 18 degrees off. That is surprising, but it's kind of in the slop of the gearing that can happen. As one unit has more hours, the teeth are going to wear in, and you're going to be off some timing. Now that said, you can, because of the gear mesh, because the crankshaft gear meshes with the cam gear, let's see if we could show this. Let's see right here. Did I download this? I think I did. Open up. Yeah. Okay. Because the cam gear, can I search cam gear? Oh yeah. Let's see if we can go in. Because the cam gear meshes with the, here's the unit pump right here, which there's 4 of those pumped by the cam. Let's see if we can find, because the cam gear meshes with the crank gear. Oh, what happened there? It's very unlikely the cam and the crank teeth would become unmeshed. It's not like it has a timing chain or a timing belt where you can slip a tooth. It's very hard for the gears to slip. But what can happen, the gear, the cam gear, this is the timing tool right here. This goes down where the unit pump goes. You remove the unit pump, and this little cup here cups to the top of the cam, locking it in top dead center. Well, here's a good spot. Let's see if we can get in here with that. So that's the timing cover. Why is it not showing that? It'll take a second to get to it. So because the cam and crank gear mesh, right, and the ignition or the timing is derived off the signals from each gear, it's possible for those to be the timing to be correct on those, but the actual mechanical timing being off, because the cam shaft can slip inside the cam gear. There's no keyway. So in other words, if you're looking, if you had a dot, one on the cam gear and one on the crank gear, they would line up indicating the engine was in time, and that's what the ECM reads as the teeth. So they would match, they would line up at the exact same spots, but the camshaft would actually be off at that moment because it slipped. So, because it's only reading the cam gear, not the actual cam shaft, and if the cam shaft slips in the cam gear, you could appear as you're in time, but you're not. I should have a picture of the front. So these unit pumps each of these go down, and fuel should flow out here. We're not getting any fuel out of that unit pump right here. We're getting fuel into the head, but we're not getting. So we're getting fuel in there. It's supposed to be like 30 psi, and we are not getting it. I'm suspecting more of unit pump issue, but timing has to be confirmed. We can't just throw unit pumps in it. But it is possible there are signs of that compression, that vacuum pulse we're speaking of. But basically, it's a test we got to do. These are all tests. So here's the mesh, the crank / cam gear. This is the crank we're reading right here. That's that teeth, those two missing teeth. So if this slipped, these teeth would be the same because this wouldn't slip, but the gear. And what would happen is if these unit pumps right here are not depressed up, or say it's telling it to fill that unit pump, but the timing is off, it's going to be trying to fill, or it's going to be blocking the fill when it should be filling. The electronic ignition could be telling it not to hey. The electronic ignition could say, hey, you're in the fill phase, so the injection is open, the port. There's a fill and a spill. There's fill, there's the spill phase. So if that timing was off, you could just flow fuel in and right out. Or the nozzle could even be closed off. It could close off fuel from entering in. I don't know how sold I am on that, but we have to check timing going forward. So here's the operation of that unit pump. So we'll go. So the roller mechanical camshaft power is located. Let's see. Two-set electrometer. The official fuel port. All right. And right here it shows the calibration code must be entered. So even if it was the pumps, John Deere has to do it. The calibration code must be entered into the ECU using Service Advisor. We don't have Service Advisor. Fuel control details. The electronic unit pump and injector nozzle is divided into 3 cycles: the fill, the pump, and the injection. So I'm trying to work out in my head if timing was off. So let's kind of go through this. The fill cycle. The fill cycle begins when the plunger A in figure 4 is pulled downward by the return spring. So if we were filling, as the roller follower follows the camshaft load, the downward motion of the plungers causes fuel from the supply galley to be drawn into the pump plunger cylinder. The unit pump solenoid E is not energized during the fill cycle, so the normally open spill valve is open. Plunger downward motion ceases when the follower reaches the base circle. So this is how I get to if the timing is off on the camshaft actually, but the ignition timing does not match the electronic timing. Let me read this again. If the pump is not energized, so the normally open spill valve is open. So what I'm saying is, if this solenoid, the pump solenoid, is actually energized, then the spill valve would be closed. Therefore, it would not be filling, or even partially filling, or depending on the severity, how far the timing is off. So again, just like if you on some pumps you press it, then the return actually draws it up. Let me think. Like let's say like a needle, you push the plunger down, but now when you pull it back out as it extends, you're pulling fuel in. But something was closing that. But they're speaking about the spill, so we got to look at the spill valve. The unit pump solenoid is not energized during the feed cycle, so the normally open spill valve is open. Okay, so now if we look at this, so they're going to say the spill valve is on F, right here. Let's see one thing. Okay. L. So this is the leak off. We're not getting any leak off. There's another port coming out of the head. So let's see. Fuel in, fuel out. I'm pretty sure that's what that is, right? So if fuel was coming in, well, that's the end of injection cycle. Let's go to the pump cycle with spill valve open. They're not showing that, are they? Okay, here we go. This may be it. I want to see the fill. All right, here we go. Piston goes down. We are going to pull fuel into here, down in. Okay. All right. Yep. So here it is right here. So this valve was closed down, right? As this extends out, it's not going to pull fuel up, over, and in through the galley there. It's not going to do that. It's not going to fill if this is blocked. Because it's seeing this line. See how that's kind of separating that? So looking like it's not going to fill. I don't know what this arrow is here. I think that's return. That looks divided. Yeah, that's that port here. All right, so the pump cycle. End of injection cycle. All right, so the pump cycle, it's going to come up. It's going to close the spill valve. It's going to close the spill valve here. And it's going to push fuel because it can't go back out. It's going to push fuel up this galley, over and down. And once it exceeds the once it exceeds the pop limit of the injector, it'll spray off. And then at the end of the injection cycle, some fuel will go back and come back out. Oh, so you can come in. So let me pause this for 1 second. All right, I'm back. Sorry about that. So yeah, trying to get at is, I think that's the same. No, that port is that. I don't get if this is actually separated. So it can come in and it can go into the nozzle. Trying to see what that actually doesn't really show. Oh, here we go. Yeah, all right, here it is, here it is. L is the return. K is the supply. So that's K. That's N. And fuel supply and return openings. Okay, supply. All right, so looking at this, fuel's coming in here. I guess fuel is just coming up here, but saying what that port's about, why that port, fuel's coming up in here. That's going to close that off to this side and pressurize that. None of this fuel. See, it doesn't show. It shows a line coming here, but this block, that's there. I guess they're the one and the same thing, maybe. And either way, well, if this was down, it would never get into there. So there is a block because they're clearly delineating. They're clearly saying that when this goes down, it's going to pull fuel up, in, and down here. But then they're saying when this drives up, it's going to push fuel out. Right? That's the end of the fill. But when it wants the pump, it's going to close that, and now nothing's going to come out. Therefore, nothing would get in to the chamber. Okay, yeah. So this is a big opening here. It's going to go around. If you close that, nothing's going to come up here and go down. I don't know why that was so hard for me to figure out. So this is all one area, but closing that, when this goes down, the vacuum that this creates will not draw the fuel in. So in other words, if that's closed, like on here, if we close this going down will not suck fuel up in here. That's the only thing I can think. I think the pumps are stuck. I think these are stuck down. And let's go back to that. The reason I think these are stuck down, I don't even know if I have that waveform. Let's see. I think I have that waveform. So I think these are stuck down. So my premise is either possibly out of timing, but even more, if this valve is down, not drawing fuel in, because if it was drawing fuel in, there's two scenarios. Either it's stuck up or stuck down. Let's go with that. Stuck up or stuck down. If they're stuck up, it'll draw the fuel in, but when it comes back up, it's just going to push it right back out, and it will push it out the return. Okay? So stuck down or stuck in, either you're not going to fill if it's stuck down, or if it's stuck in, you will fill, but then you will spill on the pump cycle. Okay? Now, the reason I know that, we'll get into this. Let me load. We'll go here, and I think I have. Let me go to the good. Let me load that. I'm going to shut off. So if I go to the injection cycle, I don't know if it's going to have it. Zoom window. Oh, zoom out. This is why I think zoom window that it's possible. This is why I think the pumps are not going. Oh, I'm going to see it on this. I think I had a better one. Hold on one second. Load data. Nope. .24 ignition coil. Load data. Zoom window. Perfect. Let me do this. This is a way to invert the waveform. Let me do this. You will see this is a good running capture. It's not much, but if you notice, I always do this wrong. Hold on 1 second. If you notice, as I'm doing this wrong. Hold on 1 second. You're going to notice on these injection waveforms that there is a little, what we call pintle hump. If you notice this little kick right here, it's not that, you got to look for it, but you can see all of a sudden it kicks out right here. That's called a pintle hump. And if you look on an injection waveform, images, it'll identify exactly what a pintle hump. Any deviation coming down shows mechanical movement of the pintle. We have that there. Now, because of the scope and the sample rate, it's not much, but you can definitely see that deviation. I have other captures where it's more pronounced, but you can see that kick out right there. You can see the kick out. I wish I may have another capture, so bear with me. You can see the kick out. The problem with this, I was using a different model scope when the sample rate was slow, but I definitely got that kick. I definitely got the kick. As opposed to, so this was a good running unit, as opposed to looking at a no start. Let me just look at one more. Actually, was this the run? This is a runner too. I may have got a better sample here. But again, I wasn't using a high enough sample rate. Actually, this was the cranking then running. Yeah, I wasn't using a high enough sample rate on this to get that, I don't think. You can still see the kick there. This is upside down. You can see that little, this is the runner. Jesus. You can see that little kick right there. You can see the little kick. So believe me when I say there is definitely a kick there, as opposed to, if I go to the no start, the no start JD, and I zoom out, and now this is this was taken with a better scope. So if I take this, you see nothing. You just see a straight slide on the no start, showing that I have no pintle movement whatsoever on that waveform. Nothing at all. These are the inverse of that waveform, and Yep, nothing, no deviation on that waveform. And you notice, you would think this is a longer cycle, so if you take cursors here, this is the one we were measuring, you can see you're on for 7 milliseconds, as opposed to on this, you're not on the whole time. You're on fully for not even a millisecond, and then you pulse for the remainder of the injection cycle. I think it's called pilot injection is what they refer to it as, to get some fuel in there. So, but again, I'm not seeing any pintle movement on those unit pumps. So I definitely think it's a 50-50 shot, and that's why injection has timing would have to be checked. And if timing looks good, then it has to move on to looking at the unit pumps and looking at the galleys that fill the unit pumps. So that's the end of this long story. And I hope I provided enough information that we were thorough. His software, my email that I sent to you, his software did a lot of verifying the ignition, that the ECM was getting the run signal, the cam and the crank signals were reporting right to the ECM. The ECM was reading it right, so it wasn't anything. It didn't show any signs of a bad ECM. So like I said, it's either timing, fuel delivery into the unit pumps, or the unit pumps themselves. I think the unit pumps are bad, and bad unit pumps can stick, causing a timing issue. So timing has to be verified, and at the end of the day, if all that even checks out good, more troubleshooting has to get done, and you would still have to remove the engine to get to repair that front engine seal leak. So no one's probably going to watch this because it ended up being 45 minutes, but who knows? Andrew will watch it. Have a good one. Adios.